Well, hello guys. So today, as the title of this video says, and the title of the screen says, we're going to look at the Fundamental Theorem of Algebra. Now, we talk about solutions to equations in A-level further maths, and more importantly, I'm going to write this out in basically university notation. So we are going to suppose that p of z is some polynomial, and I'm going to write that in summation notation from k equals 0 all the way up to the n of akz to the power k, and is a non-constant polynomial where ak is an element of the complex plane C. And of course I should note that an is non-zero. Then there is a z0 in the complex plane C, for which p of z0 is in fact 0. In other words, it tells us about the roots of a polynomial that are in the complex plane, i.e. complex roots. Now, I talked about in the end of my complex numbers lecture that the Fundamental Theorem of Algebra takes a bit to prove it. Essentially, this is the thing that we're going to try and prove right now. The proof of it is quite clever, so do stick with me. You do need elements of complex analysis to understand this, but hopefully I can try and explain it along the way. So do bear with me with this proof. So, by rescaling p, we may assume that the first an will be equal to 1. Because in my definition, I said quite clearly that an is non-zero. So I need to be slightly clever in the way that I start to prove this formula now. So if p of z is non-zero for all, upside capital A is for all, by the way, for all z in the complex plane C, it must follow that f of z is 1 over p of z. And this is an entire function. Now, if you know a little bit about topology, you'll recognize what an entire function means. If you don't worry, you don't need it to understand this too much for this particular proof, but enough of it will be helpful. Now, in order to prove this, we're going to need Liouville's theorem. So we will show that f of z is constant. Hence, p of z is constant. So, by Liouville's theorem, it suffices to show that f is bounded. That's the key word there, bounded. As such, note that f is bounded on any disk of B centered at O, radius R. So it suffices to show quite clearly using Liouville's theorem that the modulus of f of z will tend to 0 as z will tend all the way up to infinity. That is quite clearly to show that the modulus of p of z will also tend to infinity. That's z tends off to infinity. Right? The modulus of p of z is equal to, well, the modulus of z to the power n plus this infinite sum I denoted at the top of my proof, the sum from k equals 0, but I'm going to do it up to n minus 1 terms of a k z to the k, because I'm looking at the modulus, and I've already got this z to the power n that I've pulled out. And that's going to be equal to, well, the property of the modulus says I can break that z to the n out the front, and just have it as times by 1 plus this infinite sum of ak, but I've got to be slightly careful. I just have to divide by z to the n minus k to basically make sure that this counter term that I've pulled out is essentially factorable, right? And I want to put that to be greater than or equal to the modulus of z to the power n times by what's going to be 1 minus the infinite sum from k equals 0 to n minus 1, but this time I want the modulus of ak, and I want to divide that by the modulus of z to the power n minus k. If you don't know what I've done there, I'm essentially applying a triangle inequality of sort, and I'm using properties of the modulus. Again, that's always covered in the first year of your degree level, so you'll get used to manipulating these sorts of inequalities in your first year analysis. This is usually taught in second year analysis, once you have an understanding of topology, hence this proof might make a bit more sense to you. But like I say, this is just to show you what university maths is a bit like. So we can remark and say, well, since 1 over the modulus of z to the power m will tend all the way to 0 as the modulus of z tends off to infinity for any m being greater than or equal to 1, it clearly follows that for sufficient, I'll say sufficiently large, for sufficiently large mod z, say, well, we denoted up here this ball of 0 up to r. I want to use that and say, well, this modulus has to be greater than or equal to some r. We will have, let's move on to the next page here. So what will we have there? We'll have, I'm going to need that end of the thing I've wrote down, you're going to have 1 minus this infinite sum from 0 to n minus 1 of the modulus of ak divided by the mod z to the n minus k, and that's going to be greater than or equal to 1 over 2 in that case. Thus, this is pretty much the end of the proof now. For the modulus of z being greater than or equal to r, this is my final remark. We have that the modulus of p of z, well, that's going to be bigger than or equal to 1/2 of the modulus of z to the power n. And since, well, we know that mod z to the power n will tend off to infinity, as the modulus of z will clearly get larger and larger and larger, it will follow that the modulus of p of z will tend off to infinity. So we have that f of z is definitely going to be constant, and hence p of z is also constant. But we said up here that we wanted to show that the modulus of p of z will tend off to infinity as z tends to infinity. Have we shown it? Yes. We've shown it in here, right? In this last little chunk. Like I say, I've not given you all the details because you don't need them. But that is essentially the end of the proof. So if you do want me to go into much more detail about complex analysis, I will happily do videos on Liouville's theorem, and I will hopefully be seeing you in the next lecture, where we're going to spice things up a bit. I'm going to leave that hanging on what we'll talk about next time round. But yeah, as I say, that is the fundamental theorem of algebra, and that is the end of this proof.